Thank you. Good afternoon, everybody. So thank you to the organizers, the one who are here and the ones who are not here, unfortunately. Okay, so I'm going to talk about some quite recent work we did together with Moataz Abu Al-Saud and MD Chelepi. So Moataz just finished his PhD with MD and basically visited our lab for a month last year. So we just did that during this time. So I guess it's going to be quite specific about surface tension modeling. But I guess the main general point about that is that despite people have been studying surface tension models for probably 30 years or more, but there are still very basic things to do, and actually quite simple ones, to do with very basic properties of these schemes. For example, in this case, conservative in the sense of momentum conservation. So I guess that's the main general point about that, is that surface tension, of course, which is important for most of multi-phase flows we think of, I mean, at least fluid flows, is still not a solved problem in many ways. Okay, so just to remind us, what we are trying to solve. We are trying to solve the Navier-Stokes equation with surface tension. So of course the term, will this work? No, okay. So the surface tension term F gamma written here is the surface tension force per unit volume, right? The density, rho, and viscosity are material properties. They can be discontinuous across the interface, which of course poses different kind of problems. I'm not going to talk about that too much today. The surface of discontinuity, so the interface, can be represented either explicitly or implicitly. In our case, we will use implicit representation, so what is known as, let's say, front capturing type techniques. In this case, I will limit myself actually to level set type representation. I will say a word about other type of representation in the conclusions. So level set, Frederick showed a much nicer movie than my picture here about how it works. Well, the nice thing about it is that you go to a higher dimension representation, and what you gain from that is you gain implicit connectivity and topology changes. So that's nice. That's a nice feature to have. You transport a continuous field in contrast to volume of fluid where you transport a discontinuous field. So you can use standard discretization operators and you can get good convergence property for that. Of course, a big drawback is that they are not naturally mass preserving, but they have nice properties. So they are actually a nice, let's say you have a range of methods you can use to represent interfaces, and level set are definitely a very nice and useful type of method despite some drawbacks. So surface tension, so when you try to look for something new, right, very often it's interesting to go back to the basics. And going back to the basics very often means going back in time, even more than 30 years. Right? So here I go back to 1805, right? 1805 is essentially the year, 1804, 1805 is the year where Young and Laplace independently describe for the first time, let's say, the modern understanding of surface tension. What's interesting about these two papers, and I encourage you to read them, you can find, of course, Laplace, you can read in French if you read French. It's very readable. You can find the English translation of Laplace's work, of course, very easily. And they are really interesting papers for two reasons, because the first reason is that they show two different understanding of what surface tension is. So surface tension, you can think of it as, is there, you look at a flow with surface tension and there seems to be something there, right? There seems to be a film sitting between the air and the water, right? So for a long time people said, oh, there is something, there's a material interface, right? There is a real film sitting between these two things. What is this film? It's a weird thing, right? So that was essentially Young's version of it. Okay, so what you have here is a geometric interpretation of this film sitting between these two surfaces. Laplace's interpretation, of course, modern understanding of what surface tension is that he looked at cohesive forces in each of the phases and said it's the imbalance between these two cohesive forces which gives rise to this force. So there is no material interface. So in connection with this community, let's say there's a very nice connection between these concepts, is that actually Laplace's work on surface tension was one of the very strong arguments for, there's a very long discussion in Laplace's work about is matter continuous or discontinuous, which of course is very interesting from Laplace's point of view because you associate him with continuum mechanics, right? And Navier and Cauchy and so on and so forth. Even so, he was very much an atomistic person, right? There's a big debate actually at the early 19th century between Laplace's and Cauchy in particular about whether matter is continuous or discontinuous. And in connection with that, there's a fascinating article about surface tension talking about that by Maxwell in 1870, so way later, but of course at the time where Boltzmann and so on and so forth were developing kinetic theory based on this idea that matter was discontinuous or not. And of course Boltzmann thought that matter was continuous, right? To him, the discrete particle was just a mathematical artifact, right? Okay, so just aside, the history aside. So for an interface, I could go on for a long time like this, so I don't have the time. For an interface, of course, the simplest, let's say, geometric interpretation of surface tension is that it's just a force which is tangent to the material, let's say, geometric interface, right? And which is constant with a proportionally constant, which is the surface tension coefficient. If it is constant, of course, can be variable. And of course, it's what you get is a force per unit length, right? You don't get a force per unit volume. And of course, all the trick about these surface tension models is that what you can get from them is force per unit area, but what you need in the end in Navier-Stokes, formulated in a volumetric way, is a force per unit volume. So you have a missing length scale, okay? There's a problem there, okay? So let's say, if I ask you how do you then discretize, find a simple model for that, and I say you are using finite volume type technique, okay? Let's say I take the simplest example, just a square finite volume. If I ask you what is the resultant of the surface tension forces on this, well, it's easy, right? You just sum up all these tangential force, and the only place where it's unbalanced is at point A and B, where the interface exits or enters the interface. And then the surface tension force, the resultant force that you have to stick into your finite volume approximation, is just the sum of the two tangents, right, with the right sign. Okay, so that's exactly what I wrote formally here, is that the sum over the control volume omega of F sigma, the force per unit volume, okay, is equal to the sum along the curve of the force per unit length in this case, because we are in 2D. And it's just gamma b Tb minus gamma a Ta. And gamma b and gamma a are the two surface tension coefficients at point A and B. They can be different from one another, of course, if you have variable surface tension, right? So an important property, of course, of this type of construct, you see right away, is that if you integrate the surface tension force along the curve, closed curve, you get zero contribution, right? So that's what I'm talking about when I say momentum conserving, right? Is that the contribution of these forces should be zero. Otherwise, what you have is that each of your little drop has a little engine, which makes its center of mass move just due to surface tension, right? That's bad. Clearly, that's bad. Of course, that's worse because usually it's resolution dependent. So if you are trying to do multiple bubbles and droplets everywhere, you're interested in average properties, of course, average momentum transfer, you're going to use very coarse mesh, and usually this effect is going to be much worse, okay? So it's actually important even when you derive average quantities. You could say, oh, it doesn't matter, but maybe they are uncorrelated, they are random forcing, right? It's a sort of Boolean motion. But unfortunately, as usual, it's, let's say, Murphy's law, right? They are actually correlated, so your thing is actually moving around in a definite direction. So that's pretty bad. Okay. So now how do you go from this, let's say, surface or integral formulation to volumetric formulation? Well, an easy way to do that in 2D is to use the Freinet-Serre formula, which dates from 1847. So remember, it's much later than Young. Young did this calculation just considering arcs of circle. His paper is amazing because there is no drawing. He does geometric reasoning. There is no drawing in his paper. There is no equation. It's only text. Right? But it's very readable. And it does essentially the Freinet-Serre formula, but just for the particular case which interests him. So the Freinet-Serre formula relates the tangent, the derivative of the tangent along the curve, to the curvature of the curve and to the normal. So if you do that, you can integrate this force now along the normal. And if you assume now that the surface tension coefficient is constant, and it works only in this case, then you can replace that and you can transform the integral along the curve to a volume integral. To do that, you have to use a trick. You have to add this missing length scale. And of course, the mathematical trick that you use is you introduce the Dirac function, right? The Dirac function is 1 over a length scale. What is this weird length scale? Well, it's the interface thickness, which is 0, right? So you see, here we are in Dirac land, right? Dirac would be horrified, sorry, to see what we do with this function, right? Because to him it was just a mathematical trick, okay? But we still try to use it as something which is real, right? When it isn't, and that's the source of this problem. So I said that it works only if surface tension is constant. If it's not constant, you need to add, of course, the equivalent tangential force, okay? Which is still the direct term is still there, and now you have to also compute the gradient of gamma, the surface tension, along the curve, okay? Which is also itself problematic because you have a description which is volumetric, typically, like the level set function of volume of fluid, and you have to compute integral along a curve described by this volumetric function. So actually approximating this operator numerically is actually non-trivial at all. So you see there are a number of issues with this type of representation. Okay. So how do you do it in practice? How do you implement in practice this volumetric formulation? You have to find a way to represent this Dirac function. Usually what you do is that you go to the Heaviside function, right? And you take the gradient of the Heaviside, which you hope will converge to Dirac as you refine the mesh, right? And of course, you have to choose something which is differentiable. So typically you choose a smooth function, a smooth approximation to Dirac, like hyperbolic tangent or whatever, this type of functions. So what's important in there is that, of course, you have introduced an arbitrary length scale, which is this length scale epsilon, which is the interface thickness parameter, which you hope is going to converge at some point, right? So there are many formulations which are based on these basic ideas. Okay, so you can group. There are many. There are probably thousands of papers on surface tension models, right? But you can actually group most of them into two categories, this integral formulation and this volumetric formulation. So I will just give a few examples. So the classic one is the CSF model of Breck, Bill, Cossey, and Zimak, right, in '92. And what you say in this case is that you are using the volume fraction, right? And you just say that your Heaviside function is volume fraction, right? It goes from 0 to 1, and then it has a step close to the interface, so that's it, right? So that's it. Level sets, what do? You have now your distance function, okay? Your distance approximation of a Dirac. So here I give a classical example where it's using sine functions, right? And so you get a smoothly varying jumping quantity, which is based on your level set function, which is itself a continuous function, right? Not something which has a step in the middle. So that's for level set. And then another class of method you can group within there, which is much less obvious, is the Gauss-Fried method, right? So Gauss-Fried, in effect, what you do is that you assume that you know the jumps. Okay? But you can show that, even so it's obviously it's not trivial to go through the demonstration, it's actually fairly easy to show that it's exactly equivalent to choosing a different type of Dirac approximation, which is just a step function. So what's interesting about that is that very often people claim that it's a different type of representation, for example, that it's sharp versus smooth. It's actually no sharper. We'll show an example over it. It's not sharper than the other approximation. Also, another important point, if you're interested in the detail, is that it's actually identical to the first order immersed interface method of Levesque and Lee. Okay? So Levesque and Lee, their basis was studying the scheme of Peskin, right, with the delta function of Peskin. So all these schemes are actually you can group into this type of categories where, in the end, you are trying to approximate a direct delta function. Okay. So I just give a summary. So that's the summary of the various methods, right? It's more interesting to see it graphically. So graphically, it looks like that. If you look at the Heaviside function at the top, right? So you see indeed the GFM looks sharp, right? It looks like it's a sharp jump. But now when you discretize, you take the Dirac. The Dirac is the blue Dirac, right? So you see there right away that the actual thickness of the interface is, of course, similar to all the other methods. So now you are going to argue, which is the best approximation to a Dirac delta function? Well, I cannot really say, and actually it doesn't matter. So essentially, you can turn any of this method into the other one. So you could very easily turn the GFM into CSF or the other way around. You can smooth it out. It has very little influence on the results. So, we know we have tried it, and it doesn't really matter which of these approximations you choose, right? Okay, so another important property, now I switched to, I talked a bit about conservation, now I will talk a bit about well-balancing. So very important properties of these methods, actually of many types of numerical schemes, is whether they can recover particular equilibrium solution of your partial differential equation. It's not limited to surface tension. You have many type of problems where you want to recover some particular equilibrium, right? In many cases, it's not trivial, and I will explain why. It's fairly easy to understand. So at equilibrium, essentially your Navier-Stokes equation reduces to the equation at the top, which you can think of as the Young-Laplace equation written in general form, right? Which is just that the gradient of the pressure should balance the surface tension term, right? So of course it's verified for the jump of P equals to gamma times the curvature with a constant curvature, okay? This is Laplace's balance for a circular drop, okay? So what happens when you try to derive a numerical scheme? Well, in general, in a numerical scheme, you are going to make an error on grad P, okay? Which in this case, for example, I wrote as Cp, a constant, times delta square. You assume your method is second order for grade P, right? Then you will have another error, okay? Another estimate of the surface tension term, which will have, for example, a second order error. There is no reason that the two errors cancel, right? So of course they will cancel when you delta tends to 0, but that's not what you're interested in. What you're interested in is something which is close to equilibrium, even if your resolution is reasonably coarse, right? Because if you think of many cases, like in most cases you're interested in for multi-phase flows, you have drops, and you are not interested in Laplace balance, right? It's the zero order solution. What you understand is the mode of oscillations, for example, of your droplets, okay? So you need the balance first, okay? That's the condition. And that has to be achieved irrespective of spatial resolution, okay? So clearly it's not trivial. Why is it not trivial? Well, because the two terms look very different. So they are not going to be discretized using a similar scheme, right? Which is true, but if you don't do that, you get stuff like that, right? Spurious current. So I wrote 1992, 2009, right? That's the birth time and the death time of the spurious current, more or less, okay? So 1992 is the CSF paper of Bragbill, okay? And 2009 is a range of paper where essentially was solved. So it's more or less the range. So it took a long time to people to find the solution. And I will show the solution is actually very simple for the volumetric type formulation. Okay. So for volumetric formulation, the solution was actually given by Renardi and Renardi in 2002. So it took only 10 years, but to solve the details, it took a few more years. Is that now if you look at the volumetric formulation, right, you replace the direct delta times the normal by the gradient of the Heaviside function, right? So what's nice now is that now you have two gradients. You are approximating two gradients, okay? So it looks nicer because you know that you are going to be able to, if you approximate the two gradients in the same way, then the solution becomes trivial, right? I wrote nabla star is your approximation of the gradient. So it's the approximate gradient, right? You are careful to use the same approximation gradient for grade P and for grade H, okay? If you don't, that's what Bragbill et al. Did, fortunately, then it's not balanced and you get spurious currents, right? But if you do, of course, you can put all the terms inside the brackets, right? And then you get that the equilibrium solution, obviously, is P equals sigma kappa Heaviside plus a constant, which is exactly Laplace's relation, right? Okay? So you recover Laplace's relation trivially. But the big condition is that the gradient needs to be the same on both operators. So here I give an example. I mean, for staggered mesh, you just need to discretize like that and it works, right? And of course, that's again irrespective of what you choose for the Heaviside function approximation, right? Just going to condition the shape of your pressure jump, that's all. Okay, so that's a very nice property of volumetric formulations. Okay, so just a summary of that, integral formations are good because they are momentum conserving. The Marangoni stresses, let's say the variable surface tension stresses to be more accurate, are naturally included. They are exact in a finite volume sense, so I didn't really insist on that. But what happens, of course, is that if you look at it in an integral sense, the only thing which limits the accuracy with which we will get surface tension for these methods is the accuracy of the geometry description, right? If you have second order accurate tangents, you will get second order accurate results for surface tension, right? The big question is, are they well balanced, okay? Because of course we lose this relation between grade P and grade H because we don't have that anymore. We are not using the approximation anymore. So we don't have this obvious well balancing relation. As I showed before, it's not obvious that they are well balanced. Volumetric formulation, in contrast, they are not momentum conserving. You need to add the Marangoni stress. You need to approximate this term, which is not trivial. And the bad thing, really, from a, let's say, from a fundamental but also practical point of view, is that they introduce an arbitrary length scale, and they are necessarily then first order accurate, right? So these methods are first order accurate. You could say, yes, but I know how to estimate the curvature using nice operator to even fourth order. Doesn't matter. You have your grade H. Your direct delta is bad, right? It has essentially the normal you have is a crappy normal in all cases, right? It's only first order. But they are well balanced, okay? See, if you want some more, I'm doing a bit of self-promotion, but if you want some more detail here, there's an annual review of fluid mechanics where you have the whole story in more detail. Okay, so what can you do about it? Well, the first thing you can do is that you can notice that surface tension is not a body force, right? It's not something which is a volumetric force, it's a contact force. So if it is a contact force, it means it has a tensorial type expression, right? You have a stress tensor, and it can be expressed as a divergence of a stress tensor, okay? So of course that was first formulated by Cauchy, which made the distinction between body force, so if you want action at a distance, and local forces, which are indeed contact forces, okay? So what you need to look for, in the formal sense, is the stress tensor, the surface tension stress tensor, okay? So you can re-express then the integral as now the integral on the control volume of the stress tensor dot with the normal to the boundary of the control volume, right? What's nice about that is that if you do it in this way, so that's very classical, of course. Yeah, I show a standard Mach, staggered discretization, right, where you have the two velocity components as staggered. If you look at on each of the momentum control volume, or in this case I look on the horizontal momentum, right, you want to compute this integral. So what you do is that you just have the difference between sigma xx, okay, the difference between these two terms, and then the difference between the diagonal term, okay? So it's very standard in discretizing any type of stress tensor, okay? So if you do that, of course it is going to be momentum conserving. Why? Because if you look at the momentum control volume which is nearby, well, it's going to have the same term with a minus sign, so everything is going to average to 0, okay? So not only it's consistent with, let's say, Cauchy's formulation, but it's also discretely consistent, if you want, naturally, in a very natural way. You can even include that into your other stresses, of course. You could include the surface tension stress into your viscous stress or whatever. So have a single stress tensor for both. So now how do you compute the stress tensor? What is the stress tensor? Well, I gave the solution earlier, right? There is a connection, of course, between the tangential forces that you have to sum and the stress tensor. The connection is easy to do, is that when you look at the sum of these two tangent terms, right, you are looking at the intersection of the interface with the side of the control volume, okay? And actually, each of these intersections correspond to the corresponding stress tensor term, right? Which is exactly what I do here. So what I do here is I write the general form for the intersection, okay? So here gamma I Ti is the intersection with one of the control volume, and then you do that for the 4 boundaries, okay? And then you can identify each of these terms, okay, approximated with the surface tension stress tensor, okay? So that gives you the discrete expression for the surface tension stress tensor, which looks like that. So it looks simple enough. It's just gamma times the corresponding tangent divided by delta. So you say, you recover your direct delta in there. Of course, you recover a length scale. But of course, the way you recover this delta is the proper way, right? Because it's the integrally consistent way that you have the delta. Of course, this formulation is not the same. You cannot reduce that to gradient of some Heaviside function. It's not possible. So it's fundamentally different. Even so, you have introduced the length scale that you are missing, of course, but in the proper physical way. Okay, so what's nice about that, again, it's exact in a finite volume sense. It includes variable surface tension, so it has all the properties I listed before. What's nice too about it is that it only requires computation of the interface positions, okay, because you need to know where the intersection points are to be able to compute the tangent to the interface at these points, okay? It doesn't include higher order geometric properties. You don't need curvature, for example, in this case, right? So of course you can hope to have higher order estimate for tangent than for curvature, right? Of course, pressure and surface tension balance is not obvious. So that's actually not new. All I present today is not new. That's something I did 20 years ago when I was doing my PhD with Stefan Zaleski, so it's all in there. But since then, apparently nobody looked at it again, which is, well, I don't know. But so of course it was, well, in my PhD was implemented with front tracking. Front tracking is a bit complicated and people, so we said, what about level set? Level set, you can easily compute the intersection points, you can easily compute the tangents, so maybe it's simpler. And actually you can find a very simple formulation for it. Here I show only the computation of one of the component of the stress tensor, but the complexity of the other is exactly the same. So I'm not going to go through the detail, but just to give you a feeling that it's actually very simple, right? It's a bit more complicated than the gradient of the Heaviside pendulum, but not much more. So how does this work? Well, you see it's simple enough. You see at the start you have a condition which is just that are the signs of the level set function different? So is there an intersection, okay? If there is no intersection on this face, then the stress tensor component is 0, right? Because there is no contribution from that. If there is an intersection, you have essentially this term is just the interpolation, linear interpolation factor that you use, right, to linearly interpolate. Essentially it's just the distance the distance from one of the corner to the intersection point, right? And here what you have is you have interpolation of the tangential component computed from level set, okay? So here you recognize the gradient of the level set function with some linear interpolation linked to the position of the intersection point, right? And here, of course, if you have variable surface tension, you have surface tension you assume is defined at grid points, and you also need to linearly interpolate to the position of the intersection, right? This is essentially second order estimates of the quantities you have. And then there is some tricks with the sign. As you see at the bottom, you have to take into account the right sign. But essentially that's it. So it's really very simple to implement. So then the question is it well balanced? Well, we don't have a formal demonstration like in the case of a gradient of Heaviside, right? We can just try it and see if it works, right? So that's what we did here. So what I plot here is the capillary number. So if you want the velocity field, the residual velocity field that you get scaled by surface tension and viscosity as a function of time, right? So you see at the start it is not well balanced. It's not surprising because you start with a configuration which is somewhat arbitrary, but which is not exactly the numerical balancing solution. That's normal, right? And what happens after some time, so this time here, T star is scaled with the viscous dissipation time, right? So it's the viscous dissipation time scale, which is of order 1 as you expect. So what happens is that on the order of the viscous dissipation time scale, indeed you converge to something which is, you see here, 10 to the minus 15, which is actually close to machine accuracy, right? And that's, here I plotted for different resolution, spatial resolution, right? So here delta is the number of essentially 8 grid points per diameter or per radius here to 64 grid points. What you see, which is important too, is that it is independent of resolution, right? It converges somewhat faster for higher resolution, but it always converges to 0. So you don't have a resolution dependent stability, if you want, of the numerical solution. So that works nicely. I said it includes variable surface tension naturally, which is true. So a classical test case for that is you put a droplet in a temperature gradient, right? And what you have is a gradient of surface tension, okay? And then, of course, you have a little engine which drives your droplet because surface tension doesn't sum up to 0. There is an analytical solution in the Stokes regime by Young et al. In 1950s. Which gives you the analytical solution for that in the limit of low Reynolds and capillary numbers. If you do that, you get a field which is like that. So I just showed the velocity field, okay? So it's not very exciting. The drop is moving. In most cases, I showed for Laplace balance, right? It's actually the simplest solution, which are the hardest to get, right? If you have a very complicated flow with all the other stuff happening, nobody knows if it's true or not, right? If you have something which should be 0, everybody notices if there are little arrows floating around, right? So what's important here is that you see you have a nice velocity field, right? There's no little wiggles around the intervals or stuff like that, right? And of course, what you can look at is the terminal velocity. So here I plot time again scaled by another thing, which is the gradient of surface tension in effect. And the ratio between the computed and the theoretical velocity, so it should converge to 1. And what you see here is for different viscosity ratios, you see that it converges very quickly to the right solution. So on the left-hand side, it's a bit less fast for the different densities, but for the density ratio unity, you see it converges even with 16 grid point per radius. You are converged to the theoretical solution. And what's important, so I said there is lots of stuff to do. So there is a very recent paper by Serik et al., which is a nice paper where they try to improve the volumetric formulation to do exactly this test case. And I don't show the results, but they are not nearly as good as this one. So this formulation is much more accurate than the volumetric formulation. So conclusion on this. Much progress was made in the past 20 years on surface tension, but there are many things, very basic things like conservation, as I said, to be done. I believe the method presented is the first, which is conservative and well balanced. So let's say I think it's important. It's also high order. We could even push it to high order. So what we are working on at the moment is extending it to 3D. What I showed is 2D only. 3D is not fundamentally different. It's a bit more complicated, of course, because you have to deal with 3D geometry, so line integrals rather than point integral, which is a bit more tricky. Fundamentally, there is no obstacle to extending it. The big unknown is whether it's going to be well balanced or not in 3D also. Well, I didn't discuss that too much, but different choices you can make of approximations of the tangent. I saw that linearly interpolating the tangents works well. If you make other choices, it's not well balanced, right? It's still not that clear which formulation are well balanced or not. So maybe in 3D there is going to be trouble, but we don't know yet. Another thing we'd like to do is to extend to a volume of fluid interface representation. So where we are looking at here is using height function to have a clean representation of the interface locally to be able to compute intersection points and tangents. And do the same type of approach, exactly the same one. The difficulty there is that in level set you have a continuous interface representation, whereas typically in ROF you don't. And the same thing with height function. If you look at the horizontal height function, you have a nice representation, but then you need to couple it with the vertical one. So you may have problem with these continuities. So there are technical questions, but it seems it's going to work. If you are interested in the detail, it's been recently published in JCP, so that's the reference. Thank you.
All right, we're interesting. Do we have